Our video on manual metal arc stick welding follows shortly. It's just one of a series of video guides published by the Welding Institute, presenting practical information clearly and concisely on how to do the job. They're already popular over a wide range, from do-it-yourself enthusiasts to training in colleges and in industry. The first video guide showed how to set up and use a low-current MIG set, of the type which can use a small gas cylinder and be powered from a standard mains outlet. Another video guide will show you how you can get started with oxyacetylene equipment, covering safe assembly, lighting up and adjusting, welding and brazing a variety of joints, and we'll also be looking at flame cutting. If you'd like more details, just fill in and return the enclosed postcard.
Many of today's major engineering projects rely on welding to make a strong, reliable, leak-proof joint in steel for pipelines, bridges or boilers. There's a wide range of welding processes under active development, as you'll see at the end of this video. But much work of this sort is still carried out by manual metal arc welding, which has been in use for most of the 20th century. At the Welding Institute, it's one of the many processes we deal with. Here's a magnified view of the electrode as the workpiece would see it. In this video, we'll show you what you need to know to do simple jobs yourself. First, a reminder of how it works. Electric power is fed to a wire or rod of similar material to the work, which strikes an arc. The rod is supplied as an electrode, ready coated with a solid flux, but more of that at the end of the video. The end of the rod melts and deposits metal on the work to form the weld. We've said manual metal arc welding, often abbreviated to MMA. Most people call it stick welding. If people talk about electric arc welding, this is usually what they mean, but there are other types of arc welding. Americans call it shielded metal arc welding, or SMAW. We'll be showing you how to use one of these low power sets. They're all portable and work off a 13 amp socket. The controls are simple, but you should always read the instruction book carefully first. You'll need to practice before you can make a reasonable weld. We'll show you in this program how you can weld simple joints in mild steel 3 mm or more thick. We suggest you watch right through first, then look at it again in sections before you practice. Max will show you bead-on plate runs for practice and checks, how to set up the parts for welding, what to do when you're actually welding, what you might do wrong and the faults it causes, how to work safely, and how to weld up a bench with typical joints. As well as the set itself with its connecting leads, you'll need a welder's helmet or shield, a pair of stout leather gloves, a chipping hammer and clear protective goggles, a wire brush, some steel to practice on, at least 3 millimeters thick. Anything less is extremely difficult. We've used neat plates here, but you can make do with clean scrap. Of course, you'll need electrodes. We'll tell you more about these later. An electrode holder and a return clamp, and the usual workshop tools. On the set itself, there's a main switch. The main control adjusts current. The current is shown on a scale marked in amps or amperes, and usually there's an electrode diameter guide as well. You've already seen the electrode holder and return clamp. They're connected to terminals on the set, which should be tight to make good contact. Make sure the set switch is off, then plug it into the mains. The work or return cable, sometimes called the earth, is clipped to the metal workbench or job. Make sure there's a good connection on a clean area. Now for the electrode. Check the sets off first. One end of the core wire is left bare. Start with a 2.5 millimeter electrode, that is 2.5 millimeters core wire diameter. This electrode holder has several grooves in its jaws, so that you can put the electrode in at various angles to suit the job in hand. To get used to the arc, you should start by laying a weld bead on a plate. You'll need a clean piece of mild steel from 3 to 6 millimeters thick and a 2.5 millimeter electrode. Prop the metal up to stop you welding it to the bench by accident. With the current off, practice handling the electrode. You'll have to move it along, keeping it at the correct angles, 70 degrees to the line of the weld. Viewed from the other direction, it should be at 90 degrees. As well as moving the electrode along, you'll have to move it down towards the work as it gets shorter. Don't forget the correct angles. The arc will melt to the end at about this speed. So far we've shown you a right-handed welder who will work from his left to right. But if you're left-handed, you'll have to work the other way round, from your right to left. Take the electrode out of the holder and put the holder somewhere safe where it won't touch any metal parts. A cap will protect your hair against sparks. The shield is essential to protect your eyes and face. Close any gap at your neck. Max uses a paper clip. Gloves will protect your hands against burns. Make sure you have suitable clothing and that there's no flammable material nearby, and that nobody else will see the arc. Set the current to about 90 amps and switch on. Make sure you have your welding shield in position, then strike the arc. A correct run will look like this. Note the arc length. You should try to keep it about 3 millimeters long. This is what you should see from your position. To stop, backtrack over the end of the weld bead, then pull the electrode away sharply to break the arc, exaggerated here. During welding, the electrode melts at the end to form the weld. In that run, this length of the electrode was consumed to deposit this length of weld. Eye protection is essential when using the chipping hammer to remove the slag left on the weld surface. The bead should be straight and even, but you'll find a few drops of metal have stuck to the work. These are called spatter. Now, some of the things which can go wrong.
Eyes.
At first, you may find it difficult to keep the arc going when you start. It helps to scrape the electrode on the plate instead of stabbing it. If the electrode sticks to the plate, don't panic. Keep your face protected until you've broken the circuit by lifting the plate off the bench or releasing the electrode from the holder. This won't hurt the set. A poor start will leave untidy weld metal on the work. Remember, we showed you how to end the weld run by going back over the bead before breaking the arc. You don't have to do it quite as much as that, but if you just pull the electrode away, the end of the weld won't be neat and rounded, but instead will be untidy and may contain pores or cracks.
Eyes.
If the current is much too low for the size of electrode you're using, it'll be extremely difficult to strike an arc and keep it going steadily. With a bit more current, but not quite enough, even if you can keep the arc going, the weld bead will be small and lumpy.
Eyes.
When the current is too high, it'll be easy to strike the arc and keep it going, but the weld bead will be flat and spattery. With low current, the weld bead is cold. It hasn't melted into the plate. With normal current, it is smooth and rounded. With high current, it's wide, flat and spattery. If you let the arc get too long, it will go out, as well as increasing spatter and making a faulty weld.
Eyes.
And if it gets too short, the result's obvious.
Eyes.
Keeping the right travel speed is important. You may be going too fast. But if you go too slow, the weld metal piles up and may put the arc out. The beads clearly show the problems. Normal speed, fast, small and stringy, slow, large and lumpy. Another problem beginners often have is that they find it hard to move the electrode without changing the angle. They tend to hold their arms stiffly and twist their wrist. Or let the electrode sag down towards the work. Either of these faults makes it hard to control the arc. Remember, you're aiming to put down a straight, even bead. When you've been reasonably successful, you can go on to join two pieces of metal in a T-joint. Prop the pieces of metal in position and make a tack weld at each end. These are short welds to hold the pieces together while you make the main welds. Aim into the corner. Strike the arc at the end and move inwards to make a tack weld about 10 millimeters long. Clean the tack welds, not forgetting your eye protection. Prop it up at 45 degrees with the tack welds underneath. Aim the electrode at the usual 70 degrees angle to the line of weld and upright when viewed from the end. This is what the weld should look like after it's been cleaned. To get a better idea of the weld quality, at the Welding Institute we etch a cross-section. This macro section shows that the weld metal has formed a sound metallurgical bond with each part and isn't just sticking to the surface.
Eyes.
To help you make a neat start, strike an arc on a piece of scrap metal for a few seconds to heat up the electrode just before starting the job. If you didn't hold the electrode at the correct angle, or if you didn't aim it exactly into the corner, the weld metal will be on one side or the other. If the arc is too long, when you weld a joint, it's even worse than welding on a flat plate. The weld metal has a rough surface and doesn't melt in properly. The slag is trapped inside the metal. The slag and poor melting show up in a macro section. The weld will be weak. If you move along the joint too slowly, then the weld metal piles up, trapping slag underneath. normal speed. That's where Max slowed down, and here the slag prevents correct fusion. As we can see from the macro section. Next, another T-joint. If you're using a helmet, you can hold the pieces in place while you tack weld them. Instead of propping it up, leave it on the bench with the electrode at 45 degrees, otherwise weld it as before.
Eyes.
The result should be similar. This weld's rather small for the 6mm steel it's on. It won't help to get a bigger weld just by going slower. Remember what happened when we did that. One option is to use a bigger electrode if your set can supply the extra current. Another option is to make a number of runs. You make a first run, as you've already learnt, then add extra metal in 2 further runs with the electrode at different angles. It's important to clean thoroughly between runs. On a partly welded sample, this is the first run. The second run. The third run. All the runs should melt into the parts and into each other to make a complete bond. Another way of making large welds is weaving. Practice first on a flat plate, depositing metal between 2 straight weld runs, acting as a guide. Hesitate at each side. This lets the weld melt in properly. When you've finished, you should have a nearly flat pad of metal, very useful for building up worn parts. Weaving allows you to make a wide second run. With sustained arcing like this, without a cooling period, small sets may overheat, but most have protective cutouts to prevent any permanent damage. The macro section shows a good weld with a flat face, which should have a regular pattern. Next, a lap joint. You should tack weld this on the ends. Aim the electrode at 45 degrees to the vertical into the corner, as you did for the T-joint.
Eyes.
Try to put down enough weld metal to just fill up the angle. The macro section shows that the weld has just reached the top corner of the upper piece. If you don't keep the electrode aimed exactly at the corner but let it wander, the weld metal won't be in the right place, so it won't join the 2 parts. If you have problems holding a fresh electrode steady, you can save part-used electrodes for the tricky bits. Don't rest your arm on your knee or on the bench to steady it, as you'll find it's very difficult to keep the electrode at the correct angle all along the joint, which is what you should be aiming for. Instead, if you're using a helmet, you'll have a hand free to steady yourself or to support your welding hand while allowing it freedom of movement. Practice until you can make a good lap joint, then move on to a corner joint in 6mm thick steel. Start by assembling the parts with square edges so as to leave a small gap of 1 to 1.5mm. Tack weld as before at one end. Then you can unclamp the parts before tacking the other end. For the actual welding, the electrode should be upright, viewed from the end, and at 70 degrees, viewed from the side. Of course, you should aim for the centre line of the joint. If you could look at the weld from underneath, you'd see how the metal melts right through the joint. When you've finished, turn the joint over to make sure the weld metal has penetrated through to the inside. As you won't have filled the joint with metal, make a second run with weaving. Pause at the sides for good results. The macro section shows that the weld metal fills the joint with a reasonably smooth top and bottom surface. This, on the other hand, had the plates overlapping before welding, and the weld hasn't penetrated right through the joint. Here, the gap was too big, and the molten metal has penetrated too much. In fact, it could have melted right through and left a hole. Next, a butt joint between two 3mm sheets edge to edge. They shouldn't be placed touching each other, but with a gap of about 2mm, or just less than the electrode diameter. Tack weld one end as before. Then make sure the gap between the plates is parallel before tacking the other end. Prop it up above the bench, then weld it just like the bead on plate you started with.
Eyes.
This should leave a weld which extends beyond the gap between the plates. And when you look on the back, the weld metal should have gone right through and just penetrated beyond the surface. The macro section shows the smooth top and bottom profiles, and there's no sign of the original edges.
Eyes.
But if the gap was too large, or the current too high, you would burn a hole.
Eyes.
If Max finds that this is happening during welding, he flicks the electrode to put the arc out for a moment and let things cool down. On the other hand, if the current is not enough, or the gap is too small, then the weld doesn't penetrate right through to the other side. The black dot is slag, trapped inside the weld metal. To weld a butt joint in thicker metal, you'll have to grind the edges off at an angle of not less than 30 degrees. Also, grind any oxide off the surface. Leave a flat face about 1 millimetre deep to the bottom edges, and space them about 1.5 millimetres apart before tacking. This will enable you to control penetration of the first weld run.
Eyes.
Follow the first run with further runs to fill up the V groove. The macro section shows that all the runs have melted into the metal and into each other. You might need to weld vertically on jobs that can't be moved. Start by practicing putting a plain bead on a vertical plate 3 millimetres or more thick. Use a current 10 to 15 amps lower than when working flat on the bench, and weld moving upwards with the electrode coming from below at 70 degrees to the joint line. If you maintain a short arc and the correct speed, the slag will run down, but the metal should stay in position. When the slag's been cleaned off, the weld bead will be lumpier than the ones done flat. Practice until you've got a couple of reasonable beads, then move on to weaving. Again, pause at each side. Aim to weave so that you put down metal with a flat top surface. Then tackle a T-joint. If you need a larger weld, build it up by weaving, which is much easier than adding extra straight beads when welding vertically. Pause at each side to leave a flattish surface. This macro section compares a weld made flat on the bench with a straight profile and one made vertically, where it's more difficult to control. So far you've welded upwards, but for thin metal, about 3 mm, it's best to weld downwards to prevent burning through. And move fast to keep ahead of the slag. A similar butt joint in thick metal to the one welded flat is prepared in the same way and welded upwards. If Max sees the edges start to burn through, he slows down, weaves and flicks the electrode to regain control of the molten metal. Looking from the back, we can see how the weld just penetrates the joint. The weld is completed by the usual weaving runs. Next, we want to draw your attention to some essential safety precautions. Make sure your clothing won't catch fire easily. Close weave cotton fabrics are usually satisfactory, unless of course they're soaked in oil. Remove any flammable materials, that is, anything which can burn. Check anywhere that sparks could fall and be particularly careful about flammable liquids such as petrol, oil, paints or solvents. Arc welding produces a very bright light with a lot of ultraviolet. You must protect your eyes with a special filter. Shade 9 or 10 is about right for these small sets. The filter's fitted in a shield with a clear cover sheet which keeps spatter off the filter and can be cheaply replaced. The filter cuts down visible light to give you a clear view and protects your eyes from ultraviolet light. The handheld shield supplied with most sets will give adequate protection. But Max reckons it's worthwhile to buy a helmet from a welding supplier to leave a hand free to steady himself or to hold the work while tack welding, as we've already seen. Warn other people not to watch the arc unless they have a shield. Max shouts, "Eyes!" each time. Make sure all your skin is covered up, especially at your wrists and neck, to protect against ultraviolet from the arc. or you may get a form of severe sunburn. When you finish a run, remember the electrode will be hot and will also be liable to arc. So switch off or release the electrode. The electrode holder is insulated except where the electrode fits into it, and you should check that it's undamaged, whatever pattern you have. Likewise, the cable insulation. This is particularly important if you're using an industrial set, as these work at higher voltage. These small sets are liable to overheat if used at high currents, but most have a protective cutout. If this operates, just leave the set to cool down. To work for long periods at higher currents, one of the bigger industrial sets is needed. Heavier electrode holders are also used, which may have a screw clamp to hold the electrode. This pattern has a fixed electrode angle suiting some jobs, such as vertical welding, but forcing the welder to hold his arm at an awkward angle for others. To overcome this, bend the electrode, not in the middle, but next to the holder. If you bend it in the middle, the flux covering will crack off. All electrodes produce some fumes, but rarely enough to cause a problem with small sets. The fumes will go up outside your helmet if you position yourself as we suggested, but you may need to open a window to stop fumes building up if you're doing a lot of work. In factories, a special extractor takes fumes directly away from the arc region, but don't try to use your vacuum cleaner for this, it's dangerous. A final safety point, unplug and clear away any power tools from the welding bench. Now we'll see how Max welds up a sheet of steel and angle iron to make a simple bench. First, the frame for the top. The pieces have square ends. Miters would be slightly neater, but much more difficult to cut. First, Max clamps the pieces to a block, holding the ends in place for him to make 2 tack welds. He tacks all 4 corners of the frame, then checks it, both with a square and by measuring diagonals, while it's still possible to adjust it. Max has decided to put an extra bar across the middle to stiffen the top. Now he makes the final welds, holding the frame upright so as to weld the whole joint flat without stopping. The reinforcing bar is flush with the surface of the angle which will be on top. Now for the legs. Max clamps each in turn in place, then makes 3 tacks. With all 4 legs tacked, a spacer is fitted at each end. Max places the legs on the bench to make it easy to line up and weld. After tacking at one end, he can hold the other joint in place.
Eyes.
To finish welding the legs, Max makes all the joints he can before turning over to the next side. With the framework complete and any projecting welds ground flush, the last welding job is to secure the top. Max uses clamps to ensure a good fit, then makes only short welds like tack welds. These are strong enough for the job and take much less time than a continuous weld, but more importantly, a continuous weld would heat the metal much more, and the resulting expansion would distort the thin sheet. Grinding the corners smooth finishes the job. Now, more about the electrodes. The covering of the core wire has at least 3 important functions, which we'll show you. This bare wire won't maintain a steady arc at all on the usual AC supply. On DC, it'll arc all right, but as the end melts, the metal forms large, unstable drops, and there's a lot of spatter. Also, the weld metal wasn't protected from the air, so we have instant rust. But with a proper electrode, with the correct covering, the arc is steady, even on AC, metal transfers to the job in fine drops, and the coating gives off gas which protects the weld metal. There's a bewildering variety of electrodes available from welding suppliers for industrial use. They allow manual metal arc welding to cope with a wide variety of jobs with maximum weld quality and economy. As well as the electrode size, that's the core wire diameter you'll remember, coverings will be described as basic, cellulosic, rutile, some with iron powder. Electrode packets carry information on recommended current, the voltage the set should supply, whether they can be used for vertical welding, and so on. But small sets, like Max has used, supply a lower AC voltage than industrial equipment, so simply choose electrodes which are suitable for these sets. 2.5 or 3.2 mm electrodes with a rutile covering will be ideal. Because the flux is affected by moisture, electrodes should be stored in a warm, dry place, as the packet reminds you. Now we've shown you how to do your own manual metal arc welding, a glimpse of our work here at the Welding Institute near Cambridge. Close-up slow-motion photography of a MIG welding arc shows how metal is transferred from the end of the wire to the molten weld pool, and here splashes out again. A small laser hermetically seals a metal can to protect the silicon chips and other electronic components inside it from adverse environments. We also have much larger lasers which can make welds on sheets 2 mm thick or more, in this case welding right through the top sheet. To weld thicker metal with lasers, we make several runs, adding extra metal in the form of wire. Plastics are finding increasing applications in engineering, offering strength and corrosion resistance with light weight. But they may need to be joined. This is hot plate welding, used in factories and for on-site pipe welding. Friction welding is now widely used for mass production, particularly in building cars and trucks. One component is rotated against the other under pressure to generate heat. Just a few of the many advanced research and development projects going on at the Welding Institute's extensive laboratories.